Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, thank you. So now we're switching gears here, and the next talk is by Alejandro.
Thank you. The focus of this work is the representation, the semantic representation of streams. By that I mean taking streams and their content and basically writing them down in RDF, keeping all the important information that we want about the stream, but also doing so in a way that the stream will be easily accessible by RDF tools. And the first question is why would you want to do that? Well, using RDF to represent streams in a sense is the benefits are I think obvious, since RDF is a flexible, self-describing way of describing data and linking it to the metadata. The second question is why would that be a problem? After all, RDF is a model that was created supposedly to say anything about anything. So in principle it should be easy just write an ontology for streams. But as it happens, writing there are certain things in RDF that when once that you write your data like that, it's not easy to, or it's not efficient to query this data. And one of these cases in particular is anything that has to do with time, since RDF doesn't take time into account. So in particular, there's no concept of time or data changing over time. So what we try to provide in this work is a model for an RDF-based model for streams that provides an abstract representation of streams, so that once that you have your streams represented in this way, you can easily exchange, or you can easily use these streams in different systems. So creates interoperability between systems that use streams, and it does so in a way that is independent of the actual content of the stream, whether it's numeric data or text data or images. So basically, it's an homogeneous treatment of stream data, and there is that uses RDF, so you can reuse any RDF tools that you have for your data. So you could query your data using RDF query engines or RDF reasoners. So we provide a model that attempts to achieve this, and also we provide an implementation that is specifically optimized for efficient access to time series. So it's an implementation of this model based on top of other RDF stores and other semantic managers. So a few characteristics of streams that differentiate from other data is, by streams we mean sequential data that is possibly updated at a high throughput, and that is unbounded. So it's different from regular lists in RDF because it doesn't have a beginning and it doesn't have an end. And another important point is that when we are talking about streams, the data or the content of the streams is getting updated frequently, but the metadata, what we know about the stream, or where the data is coming from, stays or may stay the same. So we don't need to know, when we're talking, for instance, about data that is coming from a sensor, and we want to write the metadata about that, we can we can have constant metadata about the sensor that describe the location of the sensor or other characteristics of the sensor. But the data itself that is coming from the sensor doesn't need that much metadata. Once that you know that it comes from that sensor, you only need to know at what time it came. So a more formal definition of a string is basically a list, an unbounded list of pairs, where one of order pairs, where one element of the pair is the data itself, and the second element is a timestamp. And the timestamp, the meaning of the timestamp for the data in a stream is defined by the user. So it could be the position in the sequence, or it could be the time at what the data occurred, or the time at what the data was measured. There has been, in the last couple of years, some efforts into incorporating time into RDF by basically extending the RDF data model. Some of these efforts, one model that is getting some adoption is the model by Gutierrez, in which they essentially say that a predicate or an assertion in RDF is valid only for a certain time, and you mark that assertion as being valid only during that time. Could be an instant or an interval. And specifically for streams, there have been other attempts that essentially see RDF like a sequence of graph, or in a sense, you take the RDF graph with all your data, and you partition it in several subgraphs, where each subgraph is valid, is the data that is valid at a certain point in time. And that model works well when you're only interested in a window of data in time. So you only need to know what assertions were valid in a certain interval. But by partitioning subgraph, you're also breaking the dependencies of things that were valid at different times, and essentially things that fall in different subgraphs. Now you have no way to know that they are related. Our model is designed specifically for streams, so I think it can do better than a model that is general for time, and it's based on not saying at which time an assertion is valid, but consider that resources change over time. So essentially, resources have state, and you can talk about resources by timestamping the resource itself instead of the assertions that you make about it. And since resources in practice, these resources are associated with data, you could see this as data changing over time, and so you can easily integrate, use timestamp the resource itself, you can easily integrate the data and the metadata. So here's an example of what the model looks like. This would be data in regular RDF, indicating that there's a sensor in Chicago that measures the temperature of the day each day, and you could represent that in RDF easily enough. But when you want to query this data, you're gonna have some problems that I'm gonna explain later. So in our model, you would annotate the resource, saying this is the state of the sensor at this particular date, and when the sensor had that particular state, that state was described by these properties. So this is not only a syntax. No, it's not just syntactic sugar. Although you could translate easily between these two, this is actually a different model that says the resources have state. And you can only timestamp the subject of an assertion. You could timestamp the object. So you could say it's not easy to find an example about that, but you could say that the value of a certain property was not only a resource, but was the particular state of a resource in a particular time. So this model happens to be compatible with regular RDF. You can translate between the two using an ontology, but you can also they are semantically equivalent in the sense that whatever you can infer in one model, you can infer in the other model. So the inferences are consistent, as long as the RDF, as long as you extend RDF with interval logic or a subset of interval logic. And I said you can translate between RDF and the time annotated RDF or new RDF model using an ontology. So here's a description of the ontology. And one of the things that you should notice is that you can timestamp resources using either an instant or an interval or just a regular ordinal that represents the position of the resource in the position of the state of that resource in this sequence. So here's one example of how data looks in this model, and this would be to our model when an RDF graph is to RDF. And essentially what we're saying is that the resource has several states, and you can provide or you can make assertions about the resource in that state, but you can also make assertions about the resource in general, saying, and that would be equivalent to say that this assertion is true for the resource at all times. Now here's how the data will look translated into regular RDF, and these two are equivalent, assuming you have interval logic in RDF. So some properties of this model is that you can, as I said before, the streams can contain arbitrary data. There's no a predefined frequency for the rate at which the data appears in the streams, nor there is a beginning and an end point. So on top of this model, we also provide a query language to access to query the data in this new model. And we provide that language as an extension of Sparkle. So regular Sparkle is, as we know, the language to query, the standard language to query RDF. Now here's using the ontology to translate data to regular RDF. In regular Sparkle, this is how a query would look to ask for the current or for the last temperature at Chicago. The last temperature here means the last temperature we know of, because this string is not supposed to have an end. And this query looks fairly complicated, but although you could use a different ontology to make a simpler query on the same data, or you could rewrite this query to make it a little simpler. The point is that since the stream is unbounded, to know what is the last point in it, you have to essentially scan it and see which point doesn't have a data point after it, which is a fairly expensive operation. So in in the version in the extension of Sparkle that we provide, the query is not only simpler syntactically, but this time annotation here has a special semantic that the query engine could use to know that that data could be indexed using the timestamp, and that you could use that index to answer this query quickly instead of scanning the whole data. Now we implemented this in top of Tupelo, and there's going to be a presentation about Tupelo tomorrow, so I won't talk much about this. But Tupelo is essentially to RDF what JDBC is to relational databases. It's a framework that provides an abstraction to access different triple store and different repositories of different semantic repositories. And the interesting thing about this implementation is that Tupelo doesn't understand this new RDF. Tupelo works with regular RDF, but it's easy enough to conceptually translate between regular RDF and time annotated RDF on the fly, that you can simply put a layer on top of Tupelo and provide time annotated RDF. Also, our system integrates with other typical stream managers, but I will talk about that later. So, well, I will talk about that now. One characteristic of stream is high throughput, high rate, and there are systems that are there are systems designed specifically for handling data in real time, but and triple stores don't usually work well with data at that speed. So we provide a bridge between triple stores of RDF and stream managers like open source Data Turbine that allows you to simply fetch or publish your data using these systems that are real time, and still keep your data in RDF and query your data later in RDF. We also provide integration with fully subscribed systems like Java messaging system that allows you to do fully subscribed communication, so you can do basically event-based queries over RDF, over your RDF streams. I'm going to skip this. One example application that we have deployed using this system is it's based on virtual sensors, and what is this about is that we have data coming from a sensor, radar data, that is images from a radar, reflectivity from a radar, and that's a stream that we fetch using this system, and we process this data and publish. In this case, is the raining. Basically, this data is processed, and the results are published as a stream, and they are available. In this case, as XML, but you could have them available as RDF or some other format. So to reiterate, we provide a model for the representation of streams that is compatible with RDF to a certain extent, and a syntax for this model and a query language that includes that includes semantic queries extended with time semantics. That's it.
So we are back on time now. So we have time for questions.
I really did not understand the timestamp.
Okay.
Because in the beginning I thought you put it together with the ontology, and then I realized it seems that you were saving sensor data in RDF. Is that it?
Yes, the timestamp means that you put the timestamp in the resource, and the resource is whatever your data is. So what we're saying is that in this case the sensor is a resource. When you think of a timestamp sensor, is the state of this sensor at this point in time. So that would be the measure of the sensor. Now, the ontology is used to translate this model into regular RDF. So if you want to express, RDF doesn't have the timestamps. So if you want to express this data in regular RDF, you could use the ontology. You could translate it into RDF using the ontology. So you can represent the same thing, but you would lose some of the advantages of the model, which are in a sense, your query engine, when you're querying this data, would need to know that this ontology has a special semantics that you can use to index the data.
Okay, let me ask you a stupid question. Okay, so why not just store the data as they come from the sensors? Why go through these complicated transformations?
Well, because we want to represent the data in semantically. We not want only the data. We want the data with semantic markup in it. So.
From the larger question, the virtual sensor example is a good one for us. That we really have streaming systems that are capturing data. We'd like to have workflows that go process that data, and in some sense, we want to set the workflow to say, take the last 2 hours of data and do something with it. And so we wanted to be able to basically have the workflow make a semantic query and say, I want the last 2 hours of data, and therefore we had to take the streaming data, put it in something that we could, and the workflow engines are asking other semantic questions. So we want to have one place that could ask for what it needs in terms of time series and pull the right data out. So this is a pattern that I think we've got in lots of places where there's sensors streaming stuff in, and you want to set up workflows that just work on not give me these files and let me figure it out of band, but I really want to talk in terms of time. I want the last 2 hours, I want this sort of stuff. So that's the problem we're trying to solve with this.
So actually, follow up on that, I was wondering why limit to time and not also at location? Maybe sensor is not the right scenario, but if I think, because I doubt the sensors move physically very much, something. But like if I am a person and I have a location, I have a time, and so
that's another one we've talked about is that nobody wants, everyone wants to say, find me the sensors in Illinois or in this area. And really what you want to store at the triple level is the latitude, longitude. So you'd like to have something sitting in between a geospatial index and do the same kind of trick. So that's another area that we're looking at the same way.
Okay.